or held throughout the process of development, deployment, and regulation of trustworthy autonomous systems. So if we move to the next slide, I thought it would be useful to start off the work. I think we've moved forward one already. Can you? Yeah, I thought it'd be useful to start off the work by talking about the difference or this distinguish between different types of responsibility that exist. So here I'm distinguishing between moral notions of responsibility, causal, legal, professional, and organizational responsibility, with the view towards help these distinctions basically help us understand where gaps are in responsibility and how we would need to address those gaps with effective governance. So moral responsibility, we sort of define as blameworthiness or praiseworthiness of the actions taken by an agent. Causal responsibility is more so looking backwards and identifying the cause of an action. In legal responsibility is more so looking at how the law considers accountability for actions. And then professional responsibility, here I'm thinking more about traditional code of ethics or codes of conduct that have existed for professions to govern themselves. And then organizational responsibilities, largely how do we think about organizations within the system and the kind of collective responsibility that they have for the outcomes of their products and their services. And then I thought it was also useful to distinguish between forward-looking notions of responsibility and backward-looking notions of responsibility. So essentially, looking forward is sort of trying to meet the goals of design and duties. So how do we design with certain values in mind, and how do we meet the duties that we have towards the people that are impacted by technology? And then looking backward is more so about blaming or praising in retrospect. And the reason for including definitions of both is that the idea of good governance is concerned with both setting standards, so having standards that people must comply with, as well as holding those who do not comply accountable, and learning from past failures and improving future performance. And so this kind of feedback loop of past work and then learning from it and then improving processes in a way that ensure that we minimize harms to individuals and society. And then if we look at these distinctions I made earlier between the different types of responsibility, causal responsibility tends to be more decidedly backwards looking. So how do we now that something has occurred, figure out who should be attributed the responsibility, whereas moral and legal and professional and organizational responsibility kind of have elements of both. And what I mean by this is that in sort of the legal sense of responsibility, you have some standard setting, as well as going back and holding people accountable. And then in a professional sense, you would also have sort of codes of ethics and also ways of holding people accountable when they don't meet those. And so this is the distinction that I was trying to make here. If we move to the next slide, it's also helpful to distinguish between what is attributability, accountability, and answerability. And the reason for making this distinction is often people use the term responsibility and they mean one of these three things, but don't really specify. And I think having the clarity on what exactly we're talking about is very helpful as far as the kinds of methods and tools that we can use to effectively govern the specific type of responsibility we're talking about. So when it comes to attributability, here we're thinking about how we might assign responsibility to an agent. So not necessarily holding them to account yet, but just saying that this agent is responsible for a specific action. So one example might be a root cause analysis that occurs in an organization to figure out why there was a certain error that occurred. In accountability, here we're looking at ways of holding people accountable. And so we might require an explanation from them, or there might be some punitive damages, and this can be done in the law. As one example, accountability can also be done internally, by ensuring that certain employees are reprimanded or they require certain explanations, et cetera. And then in answerability, we're looking at the responsibility or the responsiveness of agents who were impacted by to those who are impacted by the agent's actions. So if someone was impacted, how do they have a way of potentially appealing the process or asking more of the process to understand why the certain action occurred in that way and or harmed them. And these distinctions, as I mentioned earlier, is just a way of distinguishing between the sort of strengths and weaknesses of tools that we might use for effective governance. So we might use explanation methods, for example, for attributability, but we may not fully be able to address accountability just with explainable methods. And so that's why we're making these distinctions. And then the other area where I make some distinctions are between stable behavior or expected behavior, some context-specific behavior, and then more apparent, random, or unpredictable behavior. What I mean here is more so what we see in the law and the regulatory environment, the distinguishing between foreseeable and unforeseeable actions or harms. And this is something that I think is extremely relevant and will be covered more so in the explainability and uncertainty quantification presentation that will follow after this. I think there's one more slide. One more slide. So essentially we're just that's the work that's been ongoing, is making these distinctions and working closely with other members in Pillar 2 who are working on explainability and robustness questions. And future work we see is going to include sort of a conceptual continued mapping of responsibility. So looking at different stakeholders, how might they take on responsibility within the process, and what sorts of tools might we use for governance to ensure these responsibilities within the system. And then we want to do some more applied and empirical work to look at domain-specific challenges that exist for this when we try to apply this framework to specific domains. And we want to use the industry partners that we have to think about the partner application, or how we might apply this in industry and what sorts of challenges we might run into there, and how intuitively stakeholders do understand their own responsibility and where there might be certain gaps there. So now I'll turn my presentation over to Xin, who will talk a little bit more about robustness.
So no, it is my turn, but
sorry.
It's all right. So yeah, I'm gonna give you a little bit more details about explanations, especially in healthcare domain, which is very specific. But first, I'll just give a brief introduction. Explaining machine learning models is in principle very simple, because it just consists in understanding why and how the decisions have been made. Since we are working on image classifications, so that's what will be done in healthcare domain after, explaining image classification is also in principle very simple, because it just consists of determining what part of the image has been involved in the classification process and how. There are many methods to do such explanation, and they're both they're all different. They all have their advantages, disadvantages. I'm gonna give a few examples first. On that slide, it's just a brief overview from one image of an American egret. You have three possible explanations of the model that has determined this is an American egret on that image. On the next slide, if we move on, here are more details. The first technique is called LIME, and LIME is quite a simple one and easy to run. It gives as an explanation a green and a red area on the image. The green area is what part of this image has given a correct classification when all the rest was completely blurred. And the red part is what has given a completely incorrect classification when all the rest was blurred. So we call all this area of the image the interpretable components. It can be, for example, with Lime, it is superpixels, so it's just a group of pixels. And why we want them to be interpretable is because we want to make sure that this group of pixels corresponds to something on the image. For example, on the American egret image, this is the head that is given as Lime, as the contribution of the classification. Lime is very easy to run on any model, but sometimes it's not very informative, especially because it's just it's a kind of black and white response, and the interpretable components are superpixels, which means that we need to have an expert or someone looking at the explanation and be able to determine what actually is interpretable in that green area or that red area. The second technique we've been looking at so far is called SHAP. So SHAP is a little bit more informative and more expressive because it gives the degree of contribution of interpretable components. So what is advantageous with SHAP is that these interpretable components are not necessarily superpixels. It can be features of the image, like the head of the shape of the beak or stuff like that, especially on that image. And all these little zones are isolated, and the algorithm, the SHAP, compute how much each little zone has contributed to the classification. So this gives more information because it's not black and white. It's like a degree of contribution, which is very expressive. One problem with SHAP, which is quite technical, is that we can only run it on the training data. And when we are on a specific application like healthcare domain, it means that we need to be careful with what type of machine learning model we're using and what type of data, because SHAP really relies on that. And the last example of explanation I give you is the causality-based, causal theory-based. So it just determines what is the causality between a pixel on the image and the final classification, which is a very simple way to phrase it. So what you can see on that image is a heat map of the responsibility degree of each pixel for the final classification as an American egret. This is very interesting. I think one disadvantage is that we are back to pixels or superpixels, which means that we also need an expert to have a look at the result and say, what is actually, how do we interpret this explanation? But what is very interesting with that method is that it's quite easy to run. It can be run on any model and any data. It's not like SHAP. It doesn't really rely on the choices we make. And it's based on causal theory, which is quite different and probably more closer to what we want to do in that node, because it's highly related to everything Bargavi was explaining about responsibility. On the next slide, I'm just gonna give a brief overview of what are the challenges with medical images, because the examples I've been given before are like very classical image classification examples, but medical images are more challenging. First, because it's a very different type of image. It's especially the ones we are working for cancer diagnosis and things like that. It's just patches and it's just cells, so it's patterns and things like that. We don't have features like the head of an animal or anything. It's really like a pattern. But the databases, so first, there are many databases, open databases, and it's very important for us to be able to find something we can work on, data we can work on. The databases, the data sets are very big. It's images, so it's huge, and they're annotated. So it's kind of a big pre-processing we need to make. On the top images, just give you an example. We have a big lymph nodes image which has some cancerous cells that are isolated from the rest with the little borders that are drawn. And that big image is divided into patches, and each patch is kind of one example of a border between normal cells and cancerous cells. So this pre-processing needs some work, and we need to adapt to what is proposed by the data sets we can find almost everywhere. Another problem is about the machine learning model. So the classifications algorithms are not necessarily pre-trained on such data. They are mostly pre-trained on the images we've seen before with animals or any daily basis objects, and it's definitely different to classify cancer images and classify animals. So we probably need to work on models and train our models ourselves if we want something that is relevant for the explanation. And the explanation in itself is also challenging, because there is the question of what would be interpretable components, or what would be features on such patches, because it's what I was saying before, we don't have shapes that are determined or that can be determined easily when we reach an explanation. And another question is, what explanation techniques should we use for that? Because they're all quite different in their advantages, and we need to find what is the most adapted and what would give us explanations that are interpretable enough, so we can embed them in and make them work with what we want to do in the governance nodes. And the final question is how explanations would be used, because this is not exactly the part of what I am doing, but we need to have explanations that would be able to be used and that would be practical for whoever will be using it, especially the doctors and the patients that would be provided such explanations. So when I'm talking about a final word about the explanations on medical images, is the images on the bottom. So I think it's just a quick example of what we can expect for now with the examples we've been running. So on the left, we have a proper patch with a border between the normal cells and the cancerous cells. And the idea would be to have a patch with a green zone, for example, because I've been using Lyme on that one. So a green zone which determines that this part is a cancerous cell, and this is why we can tell this image, we can detect cancer on this image. So this is what we expect as explanations, but these are just first examples. I think Shin will be explaining just after. Yeah.
Shin, are you there?
Hello, is it my turn?
Oh, yes, now we can hear you. Please go ahead.
I think this slide is not my account. Next slide, please.
So which are your slides, or whoever
Next
put these
one.
slides? Next one. So this one is still not yours.
This is about the explanation.
Okay.
I didn't put that slide. I'm sorry. I don't know who put it. But that's
Okay.
fine.
Okay. Maybe the same person who sent bogus invitations. Yeah. Okay. So this one, Shin.
Yes.
Okay.
So
go ahead.
In this research, our aim is to evaluate the current deep learning models with regard to its performance in the deployment environment. When we are talking about the deployment environment, we mean the deployment of the models for the specific tasks and the specific scenarios. In this example, we focus on the performance of the model comparing with the radiologist process, in which we would like to use the medical images, then let the model to evaluate the medical images to copy the process of radiologists. So we separate this process to different parts. So firstly is the segmentation. That's the model to localize where in the images the disease exists. And then according to the localizations, we let the model to generate the description of the disease. Then to identify the disease and to generate the report. So for the test process, we generate such unit test to check whether the model can complete the tasks, to see the performance of the model and to give an overview about how accurate and safely the model could perform on such specific scenarios. So next slide, please. So the main problem for the model in the deployment environment is the distributional shifts. When we are talking about the distributional shifts, we mean that the models, the training environments and the testing environments are different with regard to the data distributions. For example, in this data set, which is called the color MNIST, in the training environment and the testing environment, we manually add some intervention to the color of the MNIST, but keep the core digits, the shape of the digits unchanged. Then we found the modern neural networks mainly learned the association between the color and the label, rather than the shape of the digits and the label. So in this work, we focus on mitigate such kind of bias with regard to the distributional shifts to improve the robustness of the models in the deployment environment. So next slide, please. We also focus on the causal understanding of the decisions and errors in the AI-based medical diagnosis system. So the challenges are the communicating and negotiating uncertainty and its propagation through the causal chains, and how to make use of such causal knowledge to assist the decisions and to measure the potential errors more accurately, so that the model, so that we could know in which kind of situation what errors could be based on the uncertainty estimation. So next slide, please. So in this case, such kind of study decompose the error and uncertainty prediction from the model the prediction of the target labels, so that we could know exactly in which kind of situation the model could make mistake. Then in which kind of situation we would like to let the human to take over the tasks. Next slide, please. So I think this is your turn, Hannah.
Thank you. Right. So I think it's time to summarize. Looks like we are right on time. So the high level questions, right, that we are answering, just to recap, I think, and to summarize the more technical presentations that have been given now by our researchers. So we're trying to answer the following questions. So how can we show that the autonomous system behaves as intended? It doesn't behave in an unintended way. And how can we ensure behaviors of autonomous systems when they started to fail, or to explain the failure in a way that will prevent these failures in the future? Right, right, so in particular, because we have this composition of researchers in the pillar of more technical quantitative side and more ethical and qualitative side, we can discuss the questions of how should we communicate and negotiate levels of uncertainty, reliability, and risk between humans and the autonomous systems, taking into account what we can provide from the quantitative side and what we can govern from the qualitative side and from the interaction between human and the system, and how should we cope with specification responsibility gaps. So naturally, as I think it emerges already, and it's pretty clear, we cannot rely on quantitative responsibility to provide us with all the necessary features for governance. Not to mention that the specifications, I think that are going to be talked about in Pillar 3 presentation, are incomplete as well. So how are we going to cope, and what part of the work or part of the burden of regulation and governance is shifted to the human domain to complement what can be provided by the tools and by the whole framework being developed. Right, and this is just to, I borrow this from all pillars, right? So it's key areas, and we are focusing currently on case studies from medical domain with plans to extend to autonomous vehicles in the near future. Right, so questions? I think probably the questions are going to be directed to researchers, right, rather than the high-level guys of the node. So Ram, do we have time for some questions?
We have time for a couple of quick questions, and then at 12:30 we should hand over to the next session.
Okay, I cannot see the chat when I'm, so I can stop sharing and then I'll see the chat. Yeah, I think I'll stop sharing. Okay. So there was a lively discussion in the chat while we were presenting.
Do people have questions to it? I think, did you
yeah, so people that have questions. So I see there is a thread of discussion of learning lessons when things go wrong, right? And then interpretations of image. And then, so it was question to Bhargav, the previous one, this one to Benedict. And then.
So I'm not sure if Stuart is still here. So I'll
yeah, I don't know.
This question, which was at the level of the examples that Benedict had in her slides were individual image explanations. And his point was, ultimately we want system level explanations because people are not
of course.
to see the image.
So Benedict replied partly, and I also have part of the reply. I don't know, it's going to be wasted because because Stuart left, or is it still here? So anyway, so the problem of explaining a class of images is a hard problem, right? And it requires algorithms that are in principle different from explaining a single image because the question is different. So if you think, this, as Benedict showed on her example, so why is this? What was it? Okay, I'm terrible with names of birds, but let's assume it was a heron, right? Oh, he saw this here. Oh, great. So I'm not. Yeah, I feel that I'm replying to a real person. So let's assume it was a heron, right? So that image we can explain of why this specific image was classified as a heron, which depending on which approach we use, it can be, so if we mutate it a little bit, it stops being heron. So those things that we mutated, they were crucial for herons. Or the causal explanation, which is which part of the heron was sufficient to classify it as a heron and was minimal, such part, so which already produces an explanation for this classification. All of this applies to a single image. Now, if we ask, how do we explain why this class of birds is classified as herons, we are now in the domain of much more difficult questions. And this indeed is the subject of a lively research, a very active research area. And Google attempted to do this a while ago with the essence of a cat. Remember, because they let the AI study many images of cats and then to extract kind of a meta cat from it. But still, it was very easy to fool because I think it relied on the triangular ears. And in particular, so I'm currently writing also a paper about explanations of classes of images. But just a short answer is that it's a difficult problem requiring different algorithms. And but we agree that this is the problem we should tackle.
Any other questions from people? If not, I suggest we transition to the next section. Over to you, Alan.